Welcome to Pre-Calculus. Today we will investigate finding linear and angular velocity. We'll take a look at a total of 4 examples. Our first example says, find the linear velocity of a point moving with uniform circular motion if the point covers a distance s in an amount of time t. And for this specific example, we're considering that our point is moving a total distance of 3 feet and the time is 2 minutes. So we need to start off just by asking ourselves, what's linear velocity? So let's give ourselves a definition here, and we'll just bring our definition right here. So linear velocity is given by this definition. So if a point P is moving on a circle with a radius of r, and P moves a distance s along the circle's circumference in time t, its linear velocity is given by this simple equation: linear velocity v equals s divided by time. So if I just picture what's happening to my particle, this particle is moving with uniform circular motion. So let's say it's starting at a certain position and it's moving in a circular motion, and its distance is 3 feet, and it travels that distance in 2 minutes. For us to calculate linear velocity, it's really just like calculating its speed. How fast is it traveling a certain distance in a given time? So we'll just plug our information into the formula given by our definition here. So V equals S over T. So for us, our S, or our, really you can think about S, since it is in a circle, this is like arc length. And our arc length here is going to be 3 feet. The particles move 3 feet in a matter of 2 minutes. And that's going to give us, if we convert to a decimal, 1.5 feet per minute. So you can see it's got a unit that identifies it as a velocity. It's a rate, a distance over a time. So with that example, we really just have to plug in our information directly, calculate, and we've got linear velocity. Our second example is starting with different information, but working within the same definition. So here I want to find the distance s covered by a point moving with linear velocity v for a time t. So here we've got our linear velocity, it's 20 feet per second, and we're moving for a total of 4 seconds. So I'm going to bring the equation again. Linear velocity equals the arc length s, or distance, divided by t. We just need to fill in the velocity and the time, and we'll solve for the distance. So let's make those substitutions. Again, velocity here is 20 feet per second equals the distance, or the arc length s, divided by the time, which for this one is 4 seconds. So I do want to solve here for s, the distance. So I need to get s by itself. That'll solve it. So I'm going to keep that in view as I multiply both sides by 4. I need to multiply by 4 seconds to cancel this denominator. And then I'll multiply the left side by 4 seconds. So I do see another cancellation in units there. And that's important because it should give me my final unit. In this case for s, that's going to be just a distance, so feet. And I see that that's going to be left there. So as we simplify this equation, now I've got s by itself there on the right side. And for the left side, I'm just going to multiply 4 times 20. That's 80 feet. So again, what we've just discovered was if we got an object moving with uniform circular motion and it's got a velocity of 20 feet per second and it's moved for a time of 4 seconds, the distance it's traveled is going to be 80 feet. Again, within the circle. So those two examples had to do with linear velocity. Let's take a look at a couple examples that deal with a different type of velocity, angular velocity. So our third example is this one. It says point P sweeps out a central angle theta as it rotates on a circle of radius r as given below. So we've got here our theta is 2 pi over 3, and the time is for 5 seconds. What we want to find is the angular velocity of point P. So just like we did with linear velocity, we want to just give a definition to start. So angular velocity is given by this definition. So let's squeeze it in here so we can see our question and the definition. So angular velocity is given by this definition. If point P is a moving with uniform circular motion on a circle with radius r, and the line from the circle's center to that point P sweeps out a central angle theta in time t, then the point P's angular velocity, which is labeled omega, lowercase Greek omega, is given by omega equals that angle, theta, divided by time t. So let's sketch this example so that we can picture what's happening here. We've got our center of our circle, and we've got a point that's moved a central angle of 2 pi over 3. So you can recall from our investigation of radians, 2 pi over 3 is essentially 120 degrees. So it goes past 90, another 30 degrees. So roughly some path of travel like that. Let's make it a little more circular. And again, if I track that, that is my omega. So omega, I'm sorry, not my omega. Omega is the angular velocity. That's my theta. And that's my central angle, 2 pi over 3. So in that case, consider the difference between angular velocity, linear velocity. We're tracking the arc length, in this case, by the angle instead of the distance traveled. And we're traveling that kind of that central angle in a matter of 5 seconds. So we've got our definition here. The angular velocity omega is theta divided by t. I've got those two parts. So omega is going to be 2 pi over 3, that central angle, divided by 5 seconds. So I do want to simplify that fraction. I can do so by keep, change, flip. So I would keep the first fraction, 2 pi over 3, change division to multiplication, and then flip over 5. 5 is going to become 1 over 5 seconds. And what that's going to give me is 2 pi over 15. And then when I think about my units, because that angle was given in radians, I'll just put radians, rad, per second. So we do have a different unit when we're dealing with angular velocity compared to linear velocity. Our last example is, in a way, a bridge between linear velocity and angular velocity. So we're given here in our last example, number 21, for each problem below, a point is rotating with uniform circular motion on a circle of radius r. We want to find v, so again, that's our linear velocity, if the radius is 2 inches and omega, or my angular velocity, is 5 radians per second. So we need to find a common ground. How do I connect linear velocity with angular velocity? And the way that we're going to start with that bridge is just by noting that s, which again, that's the arc length or the distance traveled that we would have used in linear velocity. we have this result from trigonometry. The arc length of a path in a circle is going to equal the radius times the central angle theta. So we hadn't quite seen that result yet here, but it's in fact another result, and you would use it to calculate arc length. So it's radius times central angle. Now, to get to where we're actually relating linear velocity and angular velocity, what I would do to this equation is just divide both sides by time. So I'll divide both of these sides by time. And once I do that, really what that gives me is on the left side here, if I've got s divided by t, well, that is my definition for linear velocity. So I'm going to convert that to v. And similarly, here on the right side, theta divided by time, central angle divided by time, is how I defined angular velocity, which is omega. And this formula is really the bridge between linear velocity and angular velocity. So let me just write that here. This is the connection between linear velocity and angular velocity. And basically, linear velocity equals the radius times the angular velocity. Now, with this result in hand, we can address this question. We want to find the linear velocity v if the radius is 2 inches and the angular velocity is 5 radians per second. Very easy to do once I got my formula. So I'll just write it again. V equals r times omega. And I'm just going to plug in for radius 2 inches times angular velocity 5 radians per second. And what we're going to see here, the numbers are going to just multiply. So it's going to be 10. And then for my units, I got to kind of think radians is a lot of times a unitless measure. So I can let that radians fade away. And what we'll put for our unit here is going to be inches, 10 inches per second. And that is our linear velocity. You can tell by the units, that's a linear velocity type of unit, distance divided by time. Thank you for joining for these 4 examples, investigating linear velocity and angular velocity. See you soon.